Cutting through billions of tons of sand in one of the harshest deserts on Earth, China has created an unprecedented engineering marvel, constructing a highway stretching over 500 kilometers, with the ambition not only to connect isolated oases, but also to unlock vast resources buried beneath the desert. This project has cost approximately $260 million, mobilizing thousands of workers and engineers, operating continuously for more than 2 years under scorching temperatures that can destroy machinery, and sandstorms capable of wiping out all progress in just a few days. So how did Chinese engineers manage to build a road on a surface that never stands still? That's what we'll explore in this episode. Trapped between two massive mountain ranges in Xinjiang, the Taklamakan Desert spans more than 330,000 kilometers, one of the harshest environments humans have ever attempted to conquer. Here, surface temperatures can exceed 70 degrees Celsius in the summer and drop below -20 degrees Celsius in the winter, with almost no natural water sources and a complete absence of infrastructure. In that ocean of sand, the ground, the foundation of all construction, virtually does not exist. Sand dunes constantly shift, reshaping the terrain, and can swallow any man-made traces within just a few hours. Fine sand particles seep into every crevice, eroding materials, weakening structures, and destroying constructions from within, making all traditional building methods entirely unfeasible. But the paradox lies beneath the sand, where one of China's largest resource reserves is hidden, with more than 16 billion tons of oil and condensate, along with around 10 trillion cubic meters of natural gas, equivalent to trillions of dollars in energy value. This is not just fuel for industry, but also the foundation for electricity, petrochemicals, and the entire modern production chain. In other words, this is not just a desert, but an energy vault, locked by geography, playing a key role in China's ambition to compete for global leadership. And in that context, China had almost no other choice but to build an unprecedented highway, cutting straight through this very deadly land. But before they could build any road, they had to solve a life-or-death problem: how to make the desert stop moving. The solution Chinese engineers chose, therefore, did not begin with construction, but with understanding the desert. Across the Taklamakan Desert, survey teams were deployed for months, using high-resolution satellite imagery, ground-penetrating radar, and thousands of wind measurements to analyze sand movement patterns, wind speeds, and the terrain structure beneath the surface. Only once the route was determined could the process of desert control begin. The first step was not construction, but leveling the desert. Hundreds of bulldozers and heavy machines were deployed to cut down the peaks of tall sand dunes, moving and redistributing massive volumes of sand into lower areas to create a relatively flat and uniform surface. This process was not meant to create a complete foundation, but simply to eliminate extreme terrain fluctuations, transforming a chaotic environment into a surface that could be accessed and processed. Only then did the sand control phase truly begin. Along the planned route, thousands of workers were deployed to carry out a seemingly simple task: planting straw into the sand. Bundles of dry straw, branches, and organic materials were cut into segments, then inserted deep into the desert surface, forming a grid of evenly spaced squares with a standard size of 1 meter per side, arranged diagonally at a 45-degree angle to the prevailing wind direction. This structure, known as a checkerboard, is not a random solution. When wind blows across the desert surface, it typically accelerates near the ground, carrying sand and sweeping it away. But when it encounters this network of straw grids, the airflow is broken up, dispersed, and loses kinetic energy, causing the sand particles to no longer have enough force to keep moving. Instead of being carried away, the sand begins to settle, trapped within each small square, gradually accumulating over time and forming a more stable surface layer. This effect does not happen immediately, But after weeks and months, millions of straw grids connect into a massive network, transforming a constantly shifting ocean of sand into a controllable surface, where sand no longer moves freely, but is locked in place by a structure created by humans. That was the first turning point of the entire project. Because humans cannot stop the desert, but they have learned how to make billions of tons of sand stand still. And even then, that is still not enough to build a road that can survive in this extreme land. After the desert surface had been stabilized using the straw grid system, Chinese engineers could finally move to the next step, building a true foundation for the highway. Even when the sand had stopped moving, it was still not a foundation. It remained a loose material layer that could collapse, deform, and become unstable under the load of heavy trucks or temperature fluctuations exceeding 90 degrees Celsius between day and night. To solve this problem, they did not remove the sand, they transformed it. Along the entire route of more than 500 kilometers, groundwater was pumped from depths of 100 to 300 meters through dozens of pumping stations, then distributed via a system of pipes and nozzles, sprayed directly onto the surface with precisely controlled flow rates to allow moisture to penetrate deep into each sand layer and create bonds between particles, turning loose sand into a temporarily cohesive material mass. When the moisture reached the optimal level, heavy vibratory rollers began compacting the surface layer by layer, eliminating voids and increasing the bulk density of the sand foundation. However, this compacted sand layer was still not stable enough in the long term. Under extreme temperatures and repeated loading, it could still deform and cause uneven settlement. Therefore, the engineers added a decisive intermediate step, covering the treated sand surface with a layer of natural soil, the most important difference between the Terran highway and conventional roads. Thousands of trucks continuously transported soil from nearby areas, dumping and leveling it into a thick layer, increasing the overall weight, stabilizing the sand layer beneath, and minimizing movement under load. Only after this soil layer was completed and compacted did the reinforcement system truly begin. To prevent the mixing of material layers and control long-term deformation, engineers laid a layer of geotextile fabric across the entire surface. This fabric, typically made from polymer fibers such as polypropylene or polyester, acts as a separation and load distribution membrane, preventing the sand and soil below from intruding into the upper base layer, while helping distribute loads more evenly across the entire structure. On top of this fabric, a layer of gravel and crushed stone about 15 to 25 centimeters thick was evenly spread and further compacted, forming the primary load-bearing layer capable of distributing loads from the road surface down to the underlying foundation. In some sections, this base layer was further reinforced with stabilizing materials to enhance resistance to deformation under high temperatures. At an engineering scale, this was not just about building a foundation. It was about redefining how humans can construct on an environment that is inherently unbuildable. Because in the Taklamakan desert, the challenge is not placing a road on the surface, but creating that very surface from nothing. Once the multi-layer foundation system was finally completed, the project entered the phase that every transportation infrastructure must go through, building the road itself. But the paradox is that after everything they had done to control the desert, this turned out to be the simplest part. On top of the reinforced base, construction teams began laying the upper base material, followed by asphalt, heated and continuously transported to the site by specialized vehicles. The temperature of the asphalt mixture had to be strictly controlled, typically maintained between 140 and 160 degrees Celsius, to ensure proper workability and bonding under extreme environmental conditions. Paving machines operated continuously, spreading the asphalt into long strips, while behind them, steel rollers weighing dozens of tons immediately compacted the surface, eliminating air voids and creating a uniform structure. This process was carried out layer by layer, each layer a few centimeters thick, and was strictly tested for smoothness, compaction, and load-bearing capacity. Across the entire route of more than 500 kilometers, every meter of road was completed with high precision, ensuring it could withstand heavy truck loads and maintain stability under extreme temperature fluctuations. Expansion joints were also carefully calculated to allow the pavement to expand and contract without cracking under the desert heat. After the asphalt layer was completed, the final stages were carried out, from road markings and signage installation to drainage systems and roadside protection, all designed to adapt to the harsh desert environment. And in just over 2 years, from 1993 to October 1995, a 522 kilometers highway was completed in the heart of one of the harshest deserts on Earth, a black strip cutting across a vast ocean of golden sand, where previously almost no trace of human presence existed. But in the Taklamakan desert, finishing a road does not mean it will survive. Therefore, Chinese engineers were forced to go one step further, not just building a road, but controlling the environment around it. Along the entire highway, an unprecedented green belt system was deployed. Hundreds of thousands of trees were planted in multiple layers parallel to the road, forming a biological wall stretching hundreds of kilometers across the desert. These rows of trees are not just for landscape, they function as a natural windbreak system, reducing wind speed near the ground, trapping moving sand particles, and preventing them from reaching the road surface. As the wind slows down, the sand no longer has enough energy to pass through this barrier, forcing it to settle before reaching the highway. Groundwater is extracted from depths of over 100 meters through dozens of pumping stations along the route, then distributed through a pipeline system stretching hundreds of kilometers. Instead of flood irrigation, engineers use drip irrigation technology, delivering water directly to each tree with precise flow rates, minimizing loss under extreme heat and evaporation conditions. To sustain this entire system, more than 80 pumping stations are installed along the highway, each powered by solar panels, harnessing over 2,700 hours of sunlight per year in the region. Solar energy not only operates the water pumping system, but also turns this harsh environment itself into part of the solution. Over time, this system does not just protect the road, but also becomes an artificial ecosystem that slows desertification and creates rare green zones within the vast sea of sand. Along the entire 522 kilometers highway, maintenance is organized as a continuous operational system. Hundreds of workers and technicians are assigned to different sections, constantly monitoring road conditions, the vegetation system, and areas at risk of sand encroachment. On average, China spends around 20 to 30 million USD each year to maintain this entire system, an almost permanent cost to prevent the desert from swallowing the road. But compared to the value it brings, from unlocking trillions of dollars in resources, connecting isolated oases, to opening a continuous economic corridor across the region, that cost is simply the cheapest price to maintain control over one of China's most resource-rich regions. And from an impossible road in the desert, China has expanded its ambition, building a green Great Wall to control the desert on an unprecedented scale. From the late 1970s, China began deploying a series of mega land restoration projects that astonished the world. Instead of treating isolated erosion points, the strategy aimed to restructure the entire northern ecological belt. When northern China was left with only about 5% forest cover, the Gobi Desert stretched across northern China and Mongolia, making it one of the 6 largest deserts in the world. In 1978, the Great Green Wall project was launched, a massive artificial forest belt, also known as the tree wall, designed to create a biological shield against dust storms and restore ecosystem functions. But the core challenge quickly became clear. Planting trees in desert conditions is nothing like planting forests in humid regions. Temperatures can swing from -40 degrees Fahrenheit in winter to over 100 degrees Fahrenheit in summer, while strong winds can bury young seedlings overnight. If traditional forestry methods were applied, survival rates would be close to zero. To keep trees alive, Chinese engineers developed creative solutions. Moisture retention systems were buried deep underground to supply water over long periods. Funnel-shaped planting pits were designed to collect dew and scarce rainfall, and the sand surface was covered with mesh or straw to reduce near-ground wind speed. The selected species were not chosen for fast growth, but for extreme drought tolerance, such as saxaul, red willow, and desert poplar, with root systems capable of reaching dozens of meters down to access groundwater. The goal of the early phase was not to make the land green, but to stop the sand from moving. After more than 4 decades, China's efforts produced measurable results. By 2009, artificial forests covered about 193,000 square miles, becoming the largest man-made forest area on the planet. A 2020 report showed that this green belt absorbs large amounts of CO2, cools regional temperatures, and helps reduce the impacts of climate change. Notably, in the 1980s, the Gobi Desert had been expanding by about 3,800 square miles per year. But by 2022, it was shrinking by more than 770 square miles annually, a historic turning point. Years later, satellite data and field surveys began to show something few expected. The sand line was no longer advancing, but retreating in several monitored zones. However, some environmental scientists argue that the long-term impacts of large artificial forest belts still need continued monitoring and evaluation. From a country once mocked for being overwhelmed by advancing deserts, China has not only achieved what the United States failed to accomplish in places like the Colorado River Basin or the southwestern megadrought, but is also emerging as a major global leader in large-scale ecological engineering. What do you think about this? Slowing the advance of desertification in the Gobi does not mean China's fight against desertification is over. Gobi was only the first battlefield. As the northern greenbelt began to show results, another reality quickly emerged. The most dangerous hotspot lay farther west, in the Taklamakan Desert. Often called the Sea of Death of China, Taklamakan covers about 130,000 square miles with more than 85% made up of shifting sand dunes. In the early 2000s, sandstorms from this region repeatedly blanketed all of Xinjiang and swept into neighboring provinces, damaging roads and farmland. As a result, the Taklamakan Greenbelt project was launched. Different name, but a process largely modeled on the Gobi approach. Study the harsh climate, select drought-resistant trees, plant in grid patterns to break the wind, cover the sand with straw or mesh before planting, and install drip irrigation systems. Over more than 40 years, hundreds of thousands of workers created what many consider a miracle, as a biological belt roughly 1,715 miles long gradually formed around the desert's edge. The final 177-mile segment began construction in 2022, with the participation of about 600,000 workers and volunteers. Core species such as desert poplar, red willow, and saxaul were used to build durable windbreak strips capable of long-term sand stabilization. These tree belts also created a new economic zone, from fire-resistant wood and medicinal leaves to desert-based herbal products, all becoming stable income sources for local communities. What began as an ecological defense line has gradually turned into a livelihood belt, where environmental and economic goals increasingly intersect. It cannot be denied. China's large-scale reforestation projects are impressive, slowing desertification and placing the country among the global pioneers in desert afforestation. But as these new forests grow, a new paradox quietly emerges. While China is fighting sand, it is also fueling a massive demand for sand to build its megacities. By 2026, about 68% of China's population is projected to live in urban areas, with annual construction demand still requiring nearly 3 billion tons of sand. The problem is that desert sand is largely unusable. After long-term wind erosion, the grains are too round and too fine to form strong bonds in construction materials. That forces the building industry to turn to other sources, river sand and freshwater lake sand, where grains are more angular and provide better binding strength. The main hotspot is Poyang Lake, China's largest freshwater lake, which once covered nearly 1,700 square miles at peak season. But every day, hundreds of dredging vessels, some capable of extracting 11,000 tons per day, are cutting deeper into the lakebed. In less than 2 decades, the average water level has dropped by more than 25%. Farming areas around the lake are increasingly facing cracked soils and unstable harvests. Worse still, Poyang Lake once functioned as a natural flood buffer for the Yangtze River. With its bottom heavily dredged, summer floodwaters now move more directly downstream. A major flood could destroy more than 1 million homes. Although the Chinese government has issued bans and restrictions on sand mining since 2000, billion-dollar profits continue to drive illegal sand mining crews operating in the shadows. Controlling sand is not just ecological, it is logistical survival. Even as controversy over resource extraction grows, one reality does not change. Desert control projects cannot be stopped. To sustain the economy and develop Xinjiang's vast oil and gas reserves, China built the Taklamakan Highway in 1993, a bold lifeline cutting across the country's largest shifting sand desert. At first, it was used only to transport materials, but a few years later, it opened to residents and tourists, becoming a critical desert transport route. It did not remain a single road for long. The system expanded into 3 main branches. The primary route stretching hundreds of miles, a 97-mile side branch, and Route A at 263 miles connecting oases and strategic oil fields. The greatest challenge is not initial construction, but keeping the road alive. Under strong winds, sand dunes can shift and bury the pavement within hours. As a result, each kilometer of highway is engineered as a sand control corridor. Continuous windbreak tree belts line both sides, combined with large-scale irrigation systems to sustain vegetation in extremely dry conditions. Notably, this is China's first carbon-neutral highway system, with 109 irrigation wells and 86 solar power stations, saving about 1,000 tons of diesel fuel and 3,410 tons of CO2 each year. Where there was once only wind and sand, a ribbon of black asphalt now cuts across massive dunes, a remarkable sight. In addition, a 439-mile railway line was built, with about 90% of its length passing through areas that previously had no road access at all. Opened for freight in 2009 and for passengers in 2010, it is an engineering marvel featuring 180 bridges and more than 1,000 underpasses and tunnels. But unlike conventional railways, the main threat here is not load, it is blowing sand. To keep operations safe, China established 9 sand control centers, planted windbreak strips, and installed specialized mesh systems to stabilize dunes. Thousands of workers continuously clear sand, sometimes finishing in the morning only to see the wind cover everything again by afternoon. This steel lifeline across the desert is proof that humans can push the limits of nature. In fact, deserts, often seen as dead land, hold a major advantage. Few places receive as much solar energy. China has seized this opportunity to turn sand into massive power plants. At the edge of the Gobi Desert, one representative project is a solar thermal power plant with an energy tower about 850 feet tall, roughly the height of a 60-story building, surrounded by around 12,000 giant reflective mirrors. During the day, the entire mirror field tracks the sun and concentrates light onto the top of the central tower, generating temperatures high enough to heat molten salt storage and produce steam to drive turbines. Unlike conventional photovoltaic solar systems, molten salt thermal systems can store energy for many hours, allowing the plant to continue generating electricity even after sunset. The plant has been in operation since late 2018, with a designed output of 390 million kilowatt-hours per year. In the Kabuki Desert, the scene is even more spectacular. 196,000 solar panels arranged in the shape of a giant galloping horse, covering more than 15 million square feet, the largest energy artwork in the world, certified by Guinness. The facility has generated more than 2.3 billion kilowatt-hours of green electricity, saving about 760,000 tons of coal and reducing 1.85 million tons of CO2, equivalent to removing 400,000 gasoline cars from U.S. roads for a year. Over more than a decade, Kabuki has demonstrated that ecological economics can become a real development engine. After more than 4 decades of fighting sand, China is not stopping. The next target is 2050, to create a continuous green ring across the entire northern region and expand forest coverage by about 137,000 square miles. To achieve this ambitious goal, China is relying not only on manpower, but also on advanced technology. AI-based forest monitoring systems will track soil moisture, wind conditions, and vegetation health, while solar-powered smart irrigation systems will automatically adjust water delivery by zone. But this story is not only about China. It also serves as a map of hope for dry regions across the planet, from Africa to the American West. In your view, can this model be scaled globally to fight desertification and climate change?